falling. No air resistance, but I'll put the air streams there just to give some illusion of falling. If my potential energy is 30 joules, the unit of energy, and a potential energy of 30 joules and kinetic energy of 20 joules, what is the total energy? Not worrying about rest energy. Yeah, just add them up. As it's falling, what are the forces acting on it?
Force of gravity.
Yeah, weight. In this context, it's called weight.
Air resistance.
We're not worried about the air resistance. I'm sure you can do the Jedi thing with a pen in your hand. We're not worried about air resistance. All right, so we're done. That's the force diagram right there. We have one force in it. There's also a force pulling up on the Earth, but I don't care about that. Is weight conservative or non-conservative?
Conservative.
Since it's conservative, energy is conserved. So when the rock is now here, what is the total energy?
50 joules.
Yeah, conserved means it doesn't change. So energy is conserved. If I tell you then that the potential energy is 10 joules, therefore, what is the kinetic energy?
40 joules.
All right. Weight is acting down. This is gonna, let me connect this now to what we have over there. What is the change in potential energy?
20.
Try again.
20 joules.
That wasn't where I was getting.
Negative 20.
Yeah, negative. It's final minus initial. The change is negative 20 joules. 10 minus 30. What is the change in kinetic energy? Again, final minus initial. 20 joules. You were ahead of your time. So that's 20 joules. All right, so it makes sense if I lose, it says it's conserved. If I lost 20 joules of potential energy, it has to go somewhere. It goes to the kinetic. Now, the work done by this force, is the work done by this force, is this in the same direction? Try that again. Is this force in the same direction as the displacement or opposite? As it falls, is this in the same direction of
Opposite. Because the starting point is above, right? And then as it goes down, that'd be negative, right?
Not, well, if it's negative, the force is also negative. The question is this in the direction of displacement of the object? Cayman?
Yes.
Yeah, it is. That's the displacement right there. It goes from here to here. The force is in the same direction. So the work, conservative work being done is positive. If they're in the same direction, it's positive. So my conservative work is positive. My change in potential energy is negative. And the negative out front balances the equation. So the positive number here equals the negative of a negative. The total work done, well, I have only one force acting on it. So my total work is also positive. So I expect my change in kinetic energy to be positive. And my change in kinetic energy is positive. if the total work is positive, it's gonna get faster. If the total work is negative, it's gonna slow down. And I didn't state this explicitly, and I've implied it heavily there. If I've got a box here that I am pushing in this direction, so it goes 3 meters, and I push on it with 5 newtons of force. The work done by the 5 Newton force would be 15 Newton meters, which is 15 joules. They're in the same direction, they're parallel to each other. Life is good. If the box is moving 3 meters this way, and I'm pushing against it, so it starts out with some speed and I'm trying to slow it down, they're in opposite directions, so the work done by this 5 Newton force is negative 15 joules. If they're opposite, one of them is going to be positive, the other is negative. When I multiply them, I get a negative. Notice up here, I got 15 joules. I didn't comment which way was positive, which way was negative. They're both to the right. If I made to the right positive, then I have positive 5 times positive 3, which is positive. If to the right is negative, then I have negative 5 times negative 3, which is still positive. Questions to hear? All right. What are the chances we can get a demonstration to work well? Loop in it. Of course, I'm using massless ideal string. Probably I should put a mass on the end of it. Came undone. Come on, stop it. Now I've got both of these masses are in equilibrium. Let's see if I can. All right, both masses are in equilibrium. They're not accelerating. Matter of fact, they're in static equilibrium, in theory, if they would stop swinging. Oh, no, go move this closer to that. All right. Close enough to static equilibrium, which means in equilibrium and not moving. If I apply a mass to it, it should start to go. So if I apply a mass to this one, so assuming I have the coordination to do such, then that side will fall, the other side will rise. Hopefully that was not a shock to anyone. All right, so we'll call this mass 1 and mass 2. What are the forces acting on mass 1? And then also, what are the forces acting on mass 2? Okay. Acting which way on mass one?
Up. Weight is acting down.
And if the planet's down here, there's gonna be a weight one there. And if we did the rope, there'd be a tension acting here.
Weight is acting down on mass 2.
Weight two. Weight two.
And then
I'm putting these in and the rope in just for completeness. It's
tension
not really quite a problem.
Also pushing up, but it's less problem.
Say that again?
Tension is going up, but like
Okay.
less than mass 1.
Oh, you're saying this tension and that tension are not the same? You're not saying that, or? I was trying to interpret your
They
intention.
are not the same.
In reality, correct, but as far as we're concerned, they're the same. Ideal strength. All right, so what I really care about are this and this. Those are the ones that I care about for this. I know that the rope is not going to stretch anymore, so if that drops a meter, this is going to go up a meter. They will both move the same distance. In this is going to fall. Probably do a different color. That's going to fall some distance, X. This is going to go up some distance, the same amount. So let's take a look at the, put it somewhere. All right, so I know both of these forces will do work. This tension right here is a non-conservative force. This is a conservative force. Over here, both of these will do work because both forces are acting parallel or anti-parallel to the direction of movement. This is non-conservative, that's conservative. If I look at the total system of the work being done, since weight mass 1 is going to fall and mass 2 is going to go up, which of these two forces is doing positive work?
The displacement down is positive, right?
Yes, it doesn't matter really. It's a question of which force is in the direction of displacement. Yeah, so this is doing positive work, that's doing negative work. So the work done, so I'm looking at the total work, or otherwise known as the work, is equal to the change in kinetic energy. The work here is I have weight 1 times delta x minus my tension times delta x. Again, it's minus because the tension is up, but mass 1 is moving down. Plus, all right, down here. Which of these two forces, this is mass 2, which is going to go up, which of these two forces is doing positive work?
Tension.
So plus the tension times the distance it goes minus weight 2 times delta x. That's going to be equal to my final kinetic energy minus my initial kinetic energy. Well, let's get rid of some stuff. Those two cancel each other out. That's negative, that's positive. So the tension, even though it's non-conservative, the total non-conservative work is 0.
And don't the weight times change in x. Oh wait, never mind.
Okay.
Would it be final versus initial though, for that? For
No, it's not final versus initial on the left-hand side because they're two different masses. You want to ask your question again? You're giving the look like I missed it.
you simplify that even more?
Not really. I have weight 1 times delta x minus weight 2 times delta x is equal to 1/2 mv final squared minus 1/2 mv initial squared. Is that more simplified?
Yeah.
Okay. What's the formula for weight?
Mass times acceleration.
Say it again? I didn't quite catch all of it.
Mass times acceleration due to gravity.
There we go, all right. So we have m1g delta x minus m2g delta x equals 1/2. Now, on the right-hand side, when I'm dealing with kinetic energy, recognize both masses are moving. So that, and they move in at the same speed because the rope's not stretching. It's not like one starts to move before the other one does. Both masses have the exact same speed, not the same velocity, they're in opposite directions, the same speed. So this mass right here is mass 1 plus mass 2, v final squared, minus, I'm going to start it at rest when I do this, so minus 0, because my initial speed is going to be 0.
Is it possible that you could divide by mass 1 or mass 2?
It's not going to really help. If I divide by mass 1, this will be mass 2 over mass 1. This becomes 1 plus mass 2 over mass 1. If the masses were all the same, well, then they wouldn't move. So, but if the masses were all the same, you can get away with shortcuts there. So this is my positive work. That is my negative work. My total is just the sum of that plus this negative, or that minus that. That's the absolute value of that. So we can measure delta x. Final speed, we need to somehow figure out speed. Well, I know that if I drop an object, so if it starts from rest, so my initial speed is 0, and I drop it, if I measure how much time this takes, if I measure that time, then I have some final speed here. I know this, if I know the distance and the time, I know that that distance divided by the time is going to be my average speed. Now we've done the same before except with velocity, but since it's only going in one direction, speed is fine here. I know that my average speed is going to be 1/2 my initial speed plus my final speed. My initial speed is 0, and so my final speed is just going to be 2 times however far it falls divided by the amount of time it takes. So what we're going to do is we're going to set this up, we're going to time how long it takes to hit, and so we'll have time, we'll measure the distance, so we'll be able to calculate the speed at the bottom. The masses, we'll just trust them for now. And we'll see if we get the same thing on the left hand and the right hand side. Now I need to lower this sum so that that's on the ground. Yep, that's on the ground. So what I need to do is figure out, stay, oh, that popped off. So what I need to do is figure out how far is this going to fall, which tells me how far that's going up. So actually, that's going to fall the same distance that's going up, so that would be the same distance. Should have brought a measuring tape in here, but I did not. (132.7 centimeters). So the distance The distance it's going to go is 132.7 centimeters, or 1.327 meters. The mass, that's 200 grams, so mass 2 is 200 grams, or 0.200 kilograms. Because we are trusting the manufacturer at the moment. This is going to be 200 and, where did I think I put a 20 on there. 20. Yeah. This is 220 grams, which is 0.220 kilograms. G, I think 9.8 is sufficient for what we're doing right now. So mass 1, so this is 0.22 times 9.8 times 1.327 minus 0.20 times 9.8 times 1.327. That's going to equal 1/2 times the total mass, which is 0.42, times my final speed squared. All right, let's do it. If people can get out some stopwatches and so forth, I am going to move this around so that people can actually see it. It will be off camera for the moment. All right, do we have enough people timing? I'm going to do the classic 3, 2, 1, go. Now, if they hit each other, as this falls, if it hits that one, then we're going to have to redo it because that's going to mess things up. Yeah, it's going to miss the table. All right. 3, 2, 1, go. Did you stop it? Okay. All right, what do we got for times?
2.48.
2.33. Is there another one?
2.47.